So the theory basically tells us that these three functions have oblique, or what we call slant asymptotes. Again, the reasoning behind that is the degree up in the numerator is bigger than the degree down in the denominator, right? So that's the case for all these. So to find the end behavior, to find that slant asymptote, what we're basically going to do is actually perform the division. So here, if you recall from earlier in chapter 5, the 0 down below is -1, and if we list the coefficients, I can pretty much do this long division wise. So when I do that, what we end up getting, we'll carry the 1 down. -1 times 1 is -1. Carry that -1 down. -1 times -1 is +1, and we get -3. So this, the quotient, is x minus 1, and then we're going to add -3 all over what I divided by in the first place. And so the reason why the quotient, right, there's your slant asymptote, y equals x minus 1, is because as x gets big in either direction, right, the degree here is less than the degree there. So this part is going to go to 0, right? It's going to get smaller and smaller and smaller. So the function eventually is going to behave a lot like x minus 1 as x gets bigger and bigger and bigger in both directions. So how do I verify that? Well, let's go to technology. So here's the graph. Here's let me turn that on. So here's x squared minus 4 over x plus 1. Let me go ahead and change the colors there. Try to remember how to do this. All right, so let me make that in black. And then let's go ahead and add in there, right? I'm saying that the slant asymptote is x minus 1. And so when I go graph that, you'll notice there it is, right? So in black is the function, and in that bluish color, bluish green, there's the line x minus 1, and you can see that as x gets big positively, the graph, right, starts to hug it in that direction, the end behavior. As x gets big negatively, as we go this way, the graph starts to taper off and get closer and closer to that function. So we now know how to find that slant asymptote for the situation that we've got, right? So what about the next one? Let me turn those off. So what about the next one? Well, again, to find the slant or oblique asymptote, we do a division. Again, I'm dividing by the form x minus c. So what we learned earlier is my c is 2. We list the coefficients, and we can basically do my division. So carry the 1 down. 2 times 1 is 2. Adding, we get -4. That gives us -8, which gives us -3. So this basically is x minus 4 plus the -3 over x minus 2. Again, because x is getting big, positively or negatively, that remainder goes to 0, and so this function behaves a lot like x minus 4. So in both directions, we're going to get closer and closer to that function. So again, let's go ahead and use technology to verify what our algebra is telling us. So here's the function. Turn on. So there's the function. And what I'm going to do is add in what we claim to be the slant asymptote, x minus 4. And let me go ahead and also make sure these are in different colors. So let me put that in black. And how about I think the last one wasn't really see. How about I put that in red? So there you go. So you'll notice that again, as x gets big in a positive direction, the graph is eventually hugging the line x minus 4. As x gets big in the negative direction, the graph in black starts getting closer and closer to the line x minus 4. So we again successfully, right, our theory and our math helped us find the oblique asymptote in that situation. And then last but not least, again, we know there's some line for the next one from what we saw earlier in the module, but we have to perform the division. But unfortunately, we don't have x minus c down there. So the way we have to perform this division is by doing the good old long division. So I wanted to do an example here where it's been a while since we did long division because everything's been synthetic, but we still should know this skill. So it begins by first term into first term. Well, x times x squared does the trick, and that would give us plus x. We perform a subtraction, right? We change the signs. And so we basically get that's a 0, that's an x minus 8. So first term into first term, it doesn't. So we're looking at this being x plus x minus 8 all over x squared plus 1. And again, as x goes to infinity, both positively or negatively, because the power is 1 and the power is 2, this part's going to go to 0, right, using our slant asymptote idea. So that means that this function is going to behave a lot like y equals x. And so again, we can visualize that by graphing the function. Turn on. All right, and so I'll keep that in black. And then I'm going to add the line y equals x. And let me also put that in another color so it, oops, dang it. And there's y equals x, and you can see that it's doing exactly what we predicted would do. So as x gets big positively, the graph starts hugging y equals x. As x gets big negatively, the graph starts to hug y equals x. So there you have it. That is basically how you find, all right, theoretically, without a calculator, really quick. It's all about the degrees. So if the degree in the numerator is less than the degree in the denominator, then the x-axis is your horizontal asymptote. If the degrees are equal, it's the slant asymptote is your lead coefficient divided by your lead coefficient. And if the degree upstairs is larger than the degree downstairs, you actually perform the division to find what that oblique asymptote is, and we basically can talk about the end behavior now of our rational functions. Alright, so we're going to put this all together in a video coming soon. Talk to you guys in a moment.